Hi everyone, welcome to the next in our webinar series. It's been a great series so far where we've had speakers from both inside the Freshwater Quality Research Programme, but also speakers from outside the programme as well, including international speakers. So please do look back on some of our previous webinars if you've not had a chance to look at them. They've been really great. Just to give you a brief reminder about what the programme is trying to do. So what we're trying to do is really use the research projects within the programme, which there's 5 absolutely fantastic projects, as well as a broader set of knowledge and people to then try and strengthen our understanding of sources and behaviour of pollutants within river systems and how these are changing and accumulating with the environment and what the impacts of those pollutants are, including mixtures of pollutants. And overall, really what we want to do is use the research to inform how we go about reducing pollutant loading to river systems and the associated impacts. So this should hopefully lead to policy information that will inform policy and inform improvements to the ecological status of UK rivers and thinking particularly about how we adapt and mitigate risks, particularly from things like climate change, but also societal change and so on as well. So I mentioned the 5 projects. We have a programme champion team as well, based at Water at Leeds. And 5 absolutely super projects, all of which are multi-institutional and collaborative. And we're in the webinar series, we're now into a set of updates from each of those projects. So today we're going to hear from MOT for Rivers. But before we get to that, just a reminder that there are some links you can forward on to colleagues and so on. So there's an email address there if you want to contact us at programme level about anything. So that's freshwater@leeds.ac.uk. There's a programme website as well. And if you want to forward the information to get colleagues to sign up for our newsletter and also the webinar invites, that would be fantastic. We want to increase the community of people who are engaged with the programme and then create that long-term community of practice that allows us all to have a better shared understanding of freshwater quality. So please do spread the word as well. So just in terms of where we're up to in terms of the updates. So in April, we've got an update from the Pacific project. Then in May, the Quantum. And on the 18th of June, we've got an update from the LTLS-FE project. So please do mark those in your diary. The deal is this, which is that if you join the webinar live, then you get an opportunity to enter into discussion and ask questions and have a debate and ask probing hard stuff if you really want to. So that's what we're doing. We're recording the webinar itself, but we're not recording the Q&A just to enable people to have a more free and frank discussion. So that's the deal. If you join live, you get to partake, get to sort of have that interactive part of the webinar session. Okay, so that's it from us. Over to Andrew Tyler. It's fantastic that Andrew's presenting to us today about MOT for Rivers. Andrew's a hydronation chair for Scotland. So over to you, Andrew. Thanks.
Thank you very much, Joe. Just setting things up here. Can everybody see that all right?
Yeah, if you could put it into full presentation mode, that's it. Yeah, fantastic.
Is that okay? Good. Well, very good morning, everyone, and thank you, Joe, also for the introduction and for the opportunity to present to you the MOT for Rivers project. I should say that, like many people, I'm currently suffering from the lurgy with this persistent cough, so hopefully I'll get through this without too many interruptions. But just as a quick overview of the project, you could probably imagine, as you can see here by the authorship list, that this is a very multidisciplinary project. So I will give an overview of the project and attempt to deal with any of the detailed probing questions, but there may be a few colleagues online that may be able to help there as well, which is quite very wide-ranging, certainly very multidisciplinary in dealing with this challenge. So MOT for Rivers then is actually a result of the Hydronation Chair Programme, one which I lead, and this is a research and innovation programme funded by Scottish Water, ultimately to bring the research and innovation community together to help support that net zero ambition. And MOT for Rivers was really co-designed with Scottish Water and the wider water sector to ultimately shed new light on the interaction between climate extremes, climate change, and the increasing complexity of pollutants entering our rivers and the consequential ecosystem health. And ultimately, and most importantly, identify effective interventions to tackle these challenges. So there's quite a wide-ranging, quite an ambitious program of work that we're delivering here. So our starting point is very much on the concept of what we call the ecological safe space. And this is basically a space delimited by sort of changing hydrological, chemical, and biological stresses within which ecosystems can thrive, and beyond which, obviously, then we get deteriorations in ecosystem condition and function. Now, we're doing this by basically combining state-of-the-art science, as you might expect, but also bringing in next generation technologies as well, technologies that come to us through the innovation part of the Hydrogenation Chair programme in particular, and bringing these together to really help deliver new intelligence on hydroclimatic controls, on the fate of and impact of these increasingly complex pollutant cocktails entering into our river systems, and also understand the differential sensitivity of these ecological communities to these stresses and the impact is impacting on their structure and function, but ultimately and importantly deliver a decision support tool to test different types of interventions and adaptation strategies. Now, we're delivering this through 3 work packages, which I'll unpack a little bit more in a moment, but fundamentally we have work package 1, which is really looking at the acute impacts of climate interactions with pollutants within the river systems, and that's very much a focused digital observatory that we're building within a catchment, which is a sub-catchment to the Firth of Forth. And then we're also bringing together in work package 2 sort of state-of-the-art data analytics to look at that data that we're building in the Forth catchment, but also bring together, and most challengingly, bring together national data sets as well, so we can look at the chronic impacts of the interaction between climate and geographical gradients on that ecological safe space concept. And then fundamentally, then work package 3 brings all that learning together to deliver a decision support tool, ultimately, that will help to identify effective interventions that we can apply to mitigate some of these impacts that we're seeing. So that's the project in a whole. Let's move on. Sorry. Now, it is an ambitious program, and it's probably worth mentioning that we, in addition to building on the Hydrogenation Chair programme itself, we're building also on some substantial investments in Scotland, in particular in the Firth of Forth catchment. We are building a digital observatory of the whole of the Firth of Forth catchment, which is really looking at water, the whole water continuum in terms of water quantity and water quality. It's bringing satellite technologies together from optical and radar through to a deployment of 300 sensors across the catchment so that we can look at a series of use cases of understanding how we can manage water under a changing climate, but use that lens also to support that just transition to a net zero society as well. So we're basically building a living laboratory with all this digital data to support some of the key challenges that we have as a society. And MOT for Rivers fits very neatly into this with a use case around, obviously, water quality challenges and the interactions of climate extremes and the impact on ecosystems. Now, as I mentioned, with the Hydrogenation Chair programme, we're also building on that innovation opportunity as well. And within that, we've been working very closely with a number of startup companies. One of them is Satellite View, which is pioneering in the use of next generation satellites. It's launching a series of satellites which will enable thermal imaging at a 3-meter resolution, ultimately over the next few years, up to 12 times a day, which will, in terms of looking at waters, will be quite transformational in understanding how waters are mixing and where you might get impacts, etc., downstream to help target sampling, for example, as well as understanding the sort of the bigger processes that are occurring in our environment. So Satellite View have launched a satellite last year, had 6 months of trials with that, and then the system unfortunately failed, but it's now launching 2 more satellites next year, starting from January, and hopefully we'll bring that technology into bear with this project. We're also working with next generation, if you like, low-cost sensor manufacturers as well, and I'll talk a little bit more about those in a minute, but they are shedding new light on determinants and their behavior in the catchments in particular, giving us that potential for high-resolution monitoring of pollutants in the catchment system, and also apportioning where some of these pollutants might be coming from as well. So provenancing those, particularly exciting. And then within this program, we have an additional investment from Scottish Water to build flow-through systems where we can put in state-of-the-art sensors and also these next-generation sensors, so to test those sensors and their capabilities against the state-of-the-art capabilities, but also bring in new determinants to understand the systems in ways that we just currently can't do at the moment. And the other very important addition to this is within the catchment, which I'll talk about in a moment. We're also bringing in Scottish Water's intelligent network of sensors looking at flow and depth of water in the hydraulics in the pipework, if you like, of the urban environment around which we're building our digital observatory for this project. So we are, if you like, building already on a substantial investment. So that does enable us to try and do some very exciting things, I think, within this project in particular. So work package 1, as I've mentioned already, is really focused on looking at acute exposures of that interaction between climate extremes, floods and droughts, and pollutant cocktails and the impacts those are having on ecosystems. And we're basically bringing together that satellite capability along with high temporal resolution sensor monitoring using these flow-through systems with intensive sampling campaigns across the whole of that catchment, and using this to identify and apportion sort of rural urban sources of pollutants impacting on this particular river. It's the River Almond, but also modeling multiple contaminants transfer and interactions with the hydrology to determine routes of exposure, and ultimately also assess the sensitivity of selected organisms and ecosystems in response to these stresses, and then use this information to help drive that concept of the ecological safe space. Now, I'm often asked why the almond. I think it's important to emphasize why the almond, and it's basically typical of a UK river system. It pretty much has everything impacting upon it that you might find in other river systems across the UK. It's frequently labelled as one of Scotland's most polluted rivers, reflecting significant shifts in the economic development within that catchment from the 19th century, including some coal and shale mining, through to the electronics industries or the chemical industries, agricultural intensification, urban intensification, and also has an airport within it as well, Edinburgh Airport as well. And that results in significant gradients of pollutant hotspots and impairments across the whole of that catchment. As I said, it builds also on that smart sensor network that Scottish Water bring to this, and that's in the town of East Calder, right in the centre here, where they have 60 sensors looking at flows and water depth within the pipework of the East Calder area, which helps support the interpretation of what's actually coming out of the urban environment into the river system in particular. And as I said, we're also building complementary high-resolution flow-through systems where we are testing next-generation sensors alongside existing state-of-the-art type sensors for measuring water quality. So just to give you a bit of a perspective of our approach here in terms of the high resolution monitoring, I just need to clear my throat, sorry. Give you a chance to look at this as well. So this is, if you like, a graph of the frequency of monitoring that we're anticipating for the almond alongside the sort of parameters that we're measuring in the almond as well. So we have essentially 3 flow-through systems that we're deploying. Now we have sensors that are looking at coliform concentrations, and then we have algorithms from that to interpret the E. coli concentrations as well. And then we have a series of standard parameters as well that we might expect to measure from SONs that are being deployed in the system in particular. But as I mentioned, we're also bringing in more novel sensors as well. So, for example, using optical chemical sensing, we're working with a spin out from St Andrews University Light Water Sensors. We're developing the capability for measuring pharmaceuticals and including caffeine, for example, as well as pesticides with a sensor. And we've started to test this sensor, and it's looking very promising. I'm now deploying it with the field sampling team as well, but it hasn't yet been deployed, and I'll explain why in a moment. And we're also working with another company, Southwest Sensors, another spin out from Southampton University, which is using microfluidic technology to look at nutrients in particular. And although, for example, we have nitrate and ammonia sensors already within the platform, their sensitivity is pretty low, and these microfluidic sensors potentially have much higher sensitivity. So we're very excited to deploy those, and we're currently deploying those systems on other buoys, for example, that we're deploying within the catchment. So at the moment, though, we've had huge issues in terms of deploying and building these flow-through systems, and largely it's around permissions and getting permissions from the local authorities, etc., to deploy these, and working through huge amounts of paperwork. But we are nearly there. We had a field meeting earlier this week with all interested parties, so we're hoping that we can get on with this very quickly. We pretty much all agreed to what we need to do now, and we have a company ready and poised to start building this system for us. In the meantime, we have started sampling. So we started the sampling campaign back in September, where we're measuring the determinants already that we're anticipating for our flow-through systems, but spatially distributed across the whole of the catchment. So we have 20 sampling locations across that catchment, and also sampling further other determinants, including a whole suite of pesticides and pharmaceuticals, which I'll show you some examples from in a moment. But also we've started looking at greenhouse gas fluxes as well, looking at sort of downstream impacts potentially in terms of greenhouse gas emissions in the river system, and also collecting eDNA data as well, so as a marker of what might be happening in the biology within the river system itself. So that's happening on a monthly level. We're also on a quarterly level looking at three of the sites where we are also looking at passive sampling for other pesticides and pharmaceuticals, but also looking at sediments within the bed and sampling those for that too. And then on the 6 monthly level, we're also then sort of kick sampling and looking at macroinvertebrate surveys as well across that catchment, and at sites that are usually used for SEPA, for example, to provide continuity and that data. So we've got 8 sampling sites across the whole of that catchment. And then we're also developing a sort of capability for event-based monitoring using autosamplers, which will be positioned with the flow-through systems, because we have very large cabinets that we will be deploying on these sites. So we can actually use that to securely host autosamplers as well, and trigger those for events as they might occur. So that gives you, I think, a little bit of a snapshot of actually what we're doing and measuring. So it's not just about sensors. We are certainly doing a lot of sampling as well to support this work. So I'll just give you a very quick overview of some of the data that's coming out now. We started sampling in September, and I'll just show you some of the data that we've captured so far. Data still being analysed and being brought in, but I've got some data ready to show you, which was already looking quite interesting. This is the hydrograph data from the SEPA stations in the catchment, and you can see, for example, for each of the sampling periods, which are highlighted here in pink, the nature of the flow within the catchment. And you can see that, for example, in September and October, the flow was pretty low. But then if you look at November and December, the flow was order of magnitude higher. And so that provides a little bit of interpretation at this early stage in terms of what we might be seeing in some of the data as we move forward. So here we have data that's been presented by one of our PhD students, Bridget Rusk, who's working with us on the project as well. And she's been sampling the catchment for E. coli concentrations. And you can see here a time series animated nicely here, running through from September through to February of the E. coli concentrations within the almond, related obviously to the discharges that are occurring. So what's interesting here is that downstream, obviously, E. coli concentrations increase more broadly, but also as flow increases as well, we're also seeing higher E. coli concentrations within the catchment. And interestingly, we have some fairly high numbers here in the sort of Broxburn area of the catchment. So you can see, sorry, this part here, then the numbers do increase pretty high. And actually, we're seeing quite interesting correlations here with other determinants as well as we move forward. And one of those in particular is from our list of pharmaceuticals. And so this is paracetamol. And this is, again, at a time of low flow. And you can see actually here, paracetamol is actually effectively treated and removed in wastewater treatment works. But yet high concentrations are still being found at a time of low flow. And certainly no CSO spills either occurring into this catchment. But we're finding high E. coli concentrations just in this location. So that must be related to, sorry, I'm pointing at the wrong screen here. It must be related to some other source of sewage coming into the system, and whether that's from septic tanks or not, we don't know, but certainly needs investigating. But what is interesting, actually, even at this early stage, is that there is a very strong correlation with paracetamol and E. coli. So that paracetamol might make a good tracer for untreated wastewater entering these river systems, for example. Now, another example, just to show you very quickly, is a pesticide. So pesticides are obviously are applied intermittently within the catchment and geographically, in a way that perhaps isn't systematic in ways that we might imagine. The larger agricultural catchments are sort of higher up in this catchment in particular, but what we are finding, in fact, is very high concentrations of a particular pesticide, which I won't try and pronounce down here, but it is actually a banned neonicotinoid in the sort of Nidri burn here, which again is interesting and needs further investigation, and also the consequences of that need to be looked at as well in terms of ecosystems and its response there. So we're looking at patterns and seeing how consistent this might be and where they are occurring in the catchment. As I say, it's still very early days to draw too many conclusions from this. And then just one other example here in terms of an endocrine disruptor. Again, we are detecting these across the catchment, generally at quite low concentrations, although we do find one very high concentration at the bottom of the Goga burn, which actually drains Edinburgh Airport. And this is if I pronounce it, bisphenol A, which is associated with epoxies and also antioxidants, which might be associated with brake fluids, for example. And we may also see some of these entering other locations from draining from the road network as well. So that's quite interesting, and the consequences of that obviously need to be investigated, but hopefully it gives you a flavour, just a quick flavour of the different inputs and potential impacts that we're observing within the catchment. This is a summary of all the chemicals that are currently being tested for, and those highlighted in red are those that we've already detected within the catchment system as well. And that covers obviously the pharmaceuticals, pesticides, the neonicotinoids and the non-neonicotinoids, and also endocrine disruptors in particular. I just need another slide. Sorry. So moving on then to work package 2. And work package 2 really brings the sort of the state of the art in terms of data science techniques to understand and bring all this data together, understand sort of the sensitivity of ecological receptors to these different sources of exposure and stress, both within the almond catchment, but also at the national scale. And whilst we're sampling in work package 1 and developing that database for this part of work package 2, work package 2 is also looking at and bringing together the national databases as well to fuse and assimilate those data sets together. And that brings many, many challenges as we bring data sets together from the different regions, from the different agencies, for example. And on the right hand side here, you can actually see one of the outputs from that, some data from the Water Framework Directive on water quality that we've brought together now for the whole of the UK. And some of the challenges related to that are inconsistencies in nomenclature, in the use of determinant IDs, for example, So across the different regulatory organisations, from the Environment Agency, Natural Resources Wales, and SEPA. And so a lot of manual matching has had to be done to bring those data sets together. But we've ended up with a list of about 1,159 determinants across the three agencies, which is a huge amount of data. But essentially, by linking across and looking across these different data sets, we've actually prioritized 100 of those determinants where we have the maximum amount of data, highest or data sufficiency across the three agencies in particular, and also made sure that we've captured some of the key variables such as phosphorus and nitrogen species as well within that. We're also extracting data from the Chemical Investigations Programme. We have the data supplied by Scottish Water for Scotland, and we're currently working with UCWA to try and get that data in one from them into our system as well, and that's currently ongoing. But this next slide just gives you an overview of the different sources of data that we're capturing within this. So we're bringing together the data on the different sources of pollutants. So that's data on sort of effluent discharge, the locations of wastewater treatment works, but also in terms of diffuse pollutants as well, the land cover map for the UK, and different types of crops, and also the potentially pesticides and fertilizers used upon those as well, in terms of understanding the diffuse sources of pollutants at that national scale. Now, we're also bringing together data on the hydroclimatic controls acting on the systems in particular. So we're working with data that's obviously openly, publicly available, national scale data, and data that's also been provided by NERC and the agencies through various projects funded by NERC. And this gives you a quick overview of some of those projects, for example, that we're working from to build into this. And then in terms of pollutant cocktails, clearly working with data from the EA, SEPA, and then RW, in terms of water quality and pharmaceuticals in particular. And then again, working to build national databases to look at sort of the ecology and species and their sensitivity across the whole of the UK. So bringing in data sets that we've ourselves developed as part of the NERC Hydroscape project, which was led by one of our partners and co-Is here at Stirling, Nigel Wilby, but also other data sets, obviously from the three agencies across the UK as well. Now, the chemical database was quite challenging to pull together, but that was nothing, I think, in comparison to putting together the national database for sort of the on the biology of these river systems in particular. And that has been one of the biggest challenges that has been part of this project. So for example, and not picking on anyone in particular, but for just an example, data from SEPA didn't include any of the sort of National Biodiversity Network IDs. So records from SEPA had to be manually matched across, and also trying to automate that using our libraries as well. But matching those across to provide a consistent database has been quite a challenge, but it has been successful at least. And now it's possible to filter the whole of the databases that we have through taxonomic rank ultimately now. So we have taxonomic IDs in the data, and we can now look at the ranks across 7 different levels from kingdom to species level. And we also trying to develop unique taxonomy and export these to other databases as well. But ultimately, at the moment, this database is just going through a QA with a series of experts just to make sure that this is as correct as it can be. But we will hopefully also be able to drill down into this database to functional classes and also potentially traits as well within this data. So the other challenge is around how we deal with data, obviously from multiple different sources, which are in one sense sizable, but also very messy and diverse. And it's critical that we can also try and get a sense of the consistency that we have across these databases, or data sets in particular. And here we're building on a tool that one of our colleagues, Ruth O'Donnell, a statistician at Glasgow University, developed, so an abacus plot, which exactly provides that solution to that problem and helps us to look at consistency across these different data sets in particular. So we have created a series of plots and animations to allow us to explore these different determinants and identify their patterns and irregularities and ultimately gaps in the data across thousands of sites across the UK. And here we have some examples. So the first one here is a plot of pH across the different sites across the UK, where blue is SEPA, red is the EA, and green is Natural Resources Wales. And so this is just a plot just of pH, and actually, it reflects what you might expect to see, maybe more acidic waters, for example, in Scotland. But also, the consistency in that data set actually looks pretty good. The key, though, is the challenge around, time series of data. And on the right-hand side here, you can see another abacus plot for a given site. Is actually the Clyde, the River Clyde, and for a given determinant. And you can see that, or a given series of determinants, should I say, and you can see for all these different parameters, actually, there are still inconsistencies and gaps in that data, which presents a challenge now in terms of the next phase of actually how we fill these data gaps. So here's an animation just to demonstrate the sorts of different challenges that we have across the data. And you can see date at the bottom here, and then the site essentially going up the right-hand side here, and the spread of data that we have for a whole series of different determinants within this database. So, so you can see here, so as we move from determinant to determinant, it does vary quite dramatically across the different data sets, and obviously that then needs to be resolved, and that's the next phase of the project that we are, and particularly statisticians at Glasgow and CEH, we're working on to think about how we tackle those challenges. We are putting this data together into a web app, so everyone can actually start looking at this data, particularly the biological data here. And this is a demonstration of the app which Phil Taylor at CEH has developed, and it will allow the exploration of the biological data for river sites with records of at the taxonomic level at least. And this should be eventually available for everyone to see. And you can see here as we look at different species here, you can see where they occur and their abundance across the UK. And here we can drill down on that data and see what exists where, etc., so we can then identify what we might want to look at in particular. So as I said, this will be available fairly soon and hopefully accessible to all. So then I'll just move very quickly on to package 3. I'm nearly up on my half hour, so I'll just finish and wrap up on here now. So what package 3, as I said, really brings together the outputs from what packages 1 and 2, and it essentially develops a probabilistic risk-based meta model, bringing together those outputs to explore declining river water quality and loss of ecological safe space across the UK, both now, but also into the future. And this will also be used to develop a decision support tool that links contaminant mixtures to ecological endpoints, whilst also simulating the effect of different types of interventions and management scenarios on pollutants and pollution risk, and importantly, account for some uncertainty in that as well. Now, the decision support tool needs to be trusted and relevant, and therefore needs to be co-developed with stakeholders. And the foundation for this will be, to this approach, will be the use of Bayesian belief networks, which are very graphical and suitable for stakeholder engagement, whilst also being able to integrate qualitative and quantitative data. So we are now working on the development of the first of sort of stakeholder engagement events, particularly around the almond, and we're anticipating the first of those to be at the end of spring, maybe beginning of summer, to start the design of that decision support tool. Now, the input to this decision support tool is also critical, and the interventions are especially critical in terms of identifying what might or might not work. So at the moment, there is a review process underway, and this will be a published document at the end of this process. But at the moment, it's very much a live document to really identify, what is out there in terms of different mitigation strategies and what data exists for those different mitigation strategies, so that we can build that into that Bayesian belief network modeling program of work and use that to look at different scenarios with stakeholders and identify what might or might not work in different scenarios. So I think I've just about outlived my welcome. So I'll stop. I'll just give you a quick summary though. So in terms of where we are and what the emerging outcomes are from this project. So we are looking at very novel pollutants and bringing together new data sets at very much that high resolution acute exposure within the catchment, along with national data sets coming together for the first time in this project to really unpack that concept of the ecological safe space in particular, both at the catchment scale, but also at the national scale. These flow-through systems are also proving very popular, even though they're not up and running yet. We have a lot of interest from sensor manufacturers. We have also another European project, which this is also feeding into, which will also bring in a host of new low-cost sensors, which they would want to try and test against and benchmark against existing state-of-the-art sensors. So this is a program of work that certainly will live beyond the lifespan of MOT for Rivers to test those technologies on into the future. And ultimately, one of the key outcomes from this will be that decision support tool, which will be parameterized in a fully distributed model for the Armand catchment, so that we can look at climate change risks and the mitigation options that are available to us, but also in a semi-distributed national scale model as well, to look at risk assessments of the impact of different mixtures of pollutants and key ecological clusters and how we might mitigate those impacts in particular. And then my final slide, you'll be delighted to know, just summarizes some of the key partners that have helped within the project, but also part of our steering committee that we meet every 6 months to review the project and its progress and help support it, and also be ambassadors for the project as well. And that includes of the water industry, obviously with Scottish Water key here, but also links across the UK water industry and the water sector through both Upwear and British Water, and also UK Water Partnership, and clearly working with the statutory agencies as well. Also a key input here into the project. And we have links across to a number of other projects and initiatives as well within this. And including sort of One Health Breakthrough Partnership here in Scotland, which is working very closely with the NHS, as just an example. But I think I'll stop there and happy to try and field some of the questions. Thanks very much, everyone.